Hi, it's time for another math easy solution. And today we're going to go over a new topic in my calculus book, and that's going to be vector space in geometry. And in this first part, we're going to look at three-dimensional or 3D coordinate systems. So yes, let's jump right ahead. And note, as always, if you don't have time to watch this whole video, you can play this video at a faster speed. And here's a tutorial on that. And also, you could download and read the notes. And you could also read notes on the Hive blockchain, and that link will be in the description below. It's going to be an article format on this Hive blockchain. And also you could watch the video in parts, and the timestamps of all parts are in the description as well. Anyways, let's jump right in. So note the calculus book reference. So note that I mainly follow along the following calculus book, and that's Calculus Early Transcendental 7th edition by James Stewart. And note in the earlier videos I used the 6th edition. Yeah, so now I switched over to the 7th edition. Alright, so here's the topics to cover. So add these, I'm going to add timestamps to these, and you'll see that in the description below. So part 1 here is vectors and the geometry of space, three-dimensional coordinate systems, and then we'll look at example 1, let's remove this period, and then note on context, example 2, example 3, and then a distance formula in 3 dimensions, then example 4, example 5, equation of a sphere, and example 6, and then example 7. Alright, so let's take a look at this first part. So vectors and the geometry of space. So in this chapter, we introduce vectors and coordinate systems for three-dimensional space. This will be the setting for our study of the calculus of functions of two variables in future videos. We'll go over that in a later series, because the graph of such a function is a surface in space. So in this chapter, we will see that vectors provide particularly simple descriptions of lines and planes in space. And examples of the surfaces and solids we study in this chapter are paraboloids used for satellite dishes. So here's a parabola, 3D parabola like this, and so on. So that's a 3D parabola. There, satellite dishes, and hyperboloids used for cooling towers of nuclear reactors. So notice this setup here is a hyperbola, and then you have it in 3D, and so on. And here's added a link to different shapes here. So here is a paraboloid, here's a sphere, and here's an ellipsoid. So here's in 2D, there's a parabola, there's a circle, there's an ellipse, and there's a hyperbola. Then here's in 3D, you could have this in separate parts like that. Yeah, this one, if you look at it this way, if you look at it from that way, you'll have two parts like that. Or you could have a hyperboloid like this. And there's the equations for them. There's a sphere, there's a paraboloid, and so anyways, to continue further. So three-dimensional coordinate systems. So to locate a point in a plane, or just a flat sheet, so there's a plane like that. To locate a point, like that. What you'll need as well, two numbers are necessary. We know that any point in the plane can be represented as an ordered pair, for example, A, B, of real numbers, where A is the x-coordinate and B is the y-coordinate. For this reason, a plane is called two-dimensional. To locate a point in space, so in three-dimensional space, three numbers are required. And we represent any point in space by an ordered triplet, or an ordered triple, A, B, and C of real numbers. In order to represent points in space, we first choose a fixed point, call this O, the origin, and three directed lines through O that are perpendicular to each other, called the coordinate axis, and labeled the x-axis, y-axis, and z-axis. Usually we think of the x and y-axis as being horizontal, and the z-axis as being vertical. And we draw the orientation, not origination. So we draw the orientation of the axis as in the figure. So here's how it typically is shown. So there's the origin at the center there, and then there's the y and x as the flat plane over there, and there's the z is the vertical over there. So these are the coordinate axes. And the direction of the z-axis is determined by the right-hand rule, and as illustrated below. So there's your right hand here. Notice the thumb sticks out, and typically you could also have the index finger stick out for the x-axis. Notice it curls around here from the x to the y, and there's the vertical is your thumb. So yeah, so if you curl the fingers of your right hand around the z-axis in the direction of a 90 degree counterclockwise rotation from the positive x-axis, so from here to here is going to be at 90 degrees like that. So, or you could do it's 90 degrees like that. Just write this better. Yeah, so this is a right angle, and this is, in other words, 90 degrees like that. To the positive y-axis, then your thumb points in the positive direction of the z-axis. So these are all the positive axes like that. The three coordinate axis, the three coordinate axes or axis determine the three coordinate planes illustrated in the figure A below. So here's the coordinate planes. So this xy, we'll call this the xy plane over here, and there's the yz plane is vertical over there. And on this side, you'll have the xz plane on this side here. So those are the planes there. And here's added more text. Yeah, this is also from my calculus book. I just forgot to add it. But anyways, here. So the xy plane, so this is the xy right here, is the plane that contains the x and y axis. So there's the x and y axes. And the yz plane contains the y and z axis. So there's the z and there's the y. And the xy plane, actually, no, not the xy, the xz plane. Xz plane contains the x and z axes. And these three coordinate planes divide space into 8 parts. So you have one here, then you have another one in the back, and here, 3, 4, and then you also have on the negative sides. So you're going to have another 5, 6, 7, and then behind that is going to be 8. So you're going to have 8 parts total, and those are called octants. And the first octant in the foreground, that's this right here, this is determined from the positive axis. So those are positive ones over there. And note here, so here we have a room there, so left wall, right wall, and there's a floor, and that's because, well, many people have some difficulty visualizing the diagrams of three-dimensional figures, so you may find it helpful to do the following, and you can see this figure B above. So look at the bottom corner of a room, so let's say here, call that, and call the corner the origin. And then the wall on your left is in the XZ plane, so there's the wall there, there's left wall. And the wall on your right is the YZ plane, so there's the right wall. And the floor is the XY plane. Yeah, and the x-axis runs along the intersection of the floor and the left wall. So there's the x-axis, and then the y is on the right wall there in the floor. And the y-axis runs up from the floor toward the ceiling. Yeah, this is the... Oops, actually no, that's the z-axis. It runs up from the floor toward the ceiling along the intersection of the two walls. The y-axis runs along the intersection of the floor and the right wall. So there's the y-axis, floor and right wall. The z is in between these left and right wall and goes up that, like that. Yeah, along the intersection of the two walls. And you are situated in the first octant. So you're inside this room right here, the first one. And you'll know that there's going to be, well, 8 rooms total. And you can now imagine 7 other rooms situated in the other 7 octants, 3 on the same floor and 4 on the floor below, all connected by the common corner point here. So if you're in this room, there's going to be another one here, and then 3, and then over here, and then at the bottom, you'll have 4 more underneath you. All right. All right, so now if P, capital P, is any point in space, let A be the directed distance from the YZ plane, and from the YZ plane to P, and let B be the distance from the XZ plane to P. And this word directed, I think the calculus book just means perpendicular to it, or the shortest distance from that plane. And let C be the distance from the XY plane to P. And we'll illustrate this all soon. And then, we present the point P by the ordered triplet A, B, C of real numbers, and we call A, B, and C the coordinates of P. And A is the x coordinate, B is the y coordinate, and C is the z coordinate. Thus, to locate the point A, B, C, we can start at the origin O and move A units along the x-axis, then B units parallel to the y-axis, and then C units parallel to the z-axis as in the figure below. So we'll put all these words into a drawing to make sense of it. So you'll have this z-axis like that, the vertical one. Now you're going to have our y-axis, the positive one here, and this is the origin 0, and there is our, this is going to be perpendicular to it. This is our x-axis like that. And let's say we have a point P in space here. So it's in 3D. We'll call this point P, A, B, C. All right, so let's go make a sense of what this says. So A is directed distance from the y, z plane. So if this is the y, z plane, is this set up across on this wall? So it's a distance from that, and that's, again, that's just our x coordinate. In other words, that distance is going to be up to here somewhere. Or, yeah, so it's going to be up to here. But before that, so let's say we have this. I'm going to draw this all the way down here, all the way to the bottom. And then, yeah, so let's say it hits the bottom here. And then draw this perpendicular. It's going to go all the way across here, like that. Oops. Yeah, and this is parallel to this one right here. So this is parallel to this wall. And this one here is parallel to this, like that. Yeah, so then this distance from the ZY plane is the x-coordinate, and in other words, we can start from the origin 0 and move A units along the x-axis. So there's the A units, and then B units parallel to the y-axis, that's B, like that, and then C units parallel to the z-axis, like this. So B is going to be, this distance B is the distance from the ZX plane, or the XZ plane. XZ plane is B. And then C is the distance from the XY plane to P. So this is the XY plane, and there's a Z. This is C, not Z. Like that. And then C distance all the way up to there. Alright, so going further, so the point ABC determines a rectangular box, as in the figure below. So we have this right here. Let's draw this again, but now you can see that this can form a rectangular, a rectangular box. So we'll do that again. So we have the Z, like that, and then we're going to have our y. I'm just going to make this, yeah, it's a bit shorter. So this is our y, and then this is going to be our x, like this. Whoops, this is going to be our x, like that. And let's say we have our point P across here. So this is our point P, and we're going to have a box. So let's draw this all in 3D. This goes down here. This goes, draw this a bit neater. So this is, let's say it goes here, and there is the line across, there's the line across, and then draw this all in 3D, like that. And then this goes across like that. This goes like that. There is our 3D box. All right, so there's our box, and this one we're going to call this P, A, B, C. All right, continuing further. So if we drop the vertical perpendicular line from P to the XY plane, so if we drop this line, just remove that. In other words, our vertical distance C becomes 0. We get a point Q with coordinates A, B, and 0 called the projection of P onto the XY plane. So that's this point right here. This is our point Q, like that. And we'll call this A, B, and then the vertical distance is 0, like that. And similarly, R, 0, B, C, and R, the points are A0, A0, C are the projections of P onto the YZ plane and XZ plane, respectively. So in other words, this one we're going to remove the this A value. That's this horizontal X coordinate from here to here. So in other words, we're going to get this point here. So actually, no, this one here. We're removing it, so we get this point here. This one's going to be our R, and then the X coordinate is 0. Everything else is the same, B and C, like that. And that's a projection onto the Z, onto the YZ plane. And that's right here, YZ plane. And then the next one is our S. We're going to drop this down. Yeah, we're going to drop the Y coordinate. So we're going to project it all the way onto this XZ plane, so the XZ plane. So we're going to drop this line, and we're going to go all the way up to here. So this is P, Q, R, and this one is S, like that. Now let's put this like this. This is going to be our S. This is going to be our A. 0 is the Y coordinate, and then this is going to be C, like that. All right, continuing further, so as numerical illustrations, the points right here, -4, 3, -5, and 3, -2, -6 are plotted in the figures below. So let's graph this one, or let's plot that point out first. So this one is, notice it's going to go -4, so we're going to go the negative x-axis, then it's going to be positive 3, and then this is negative. So in other words, it's going to be on the below these axes. This is the z, it's going to be a negative one. So let's say we have our y like this, and we're going to have to extend this all the way down because it's going to be negative z. Just extend this down further. And we're also going negative x, so that's going to go backwards. So we're going to have to go from here. This is our x, but then we're going to have to go to the backwards side of it. So we're going to go -4. So let's put it all the way here. So we're going to go -4. And let's put that line here. And then we're going to go, so let's say all the way up to here. And then we're going to go +3 to the y. Make it a bit shorter than that. So let's make it here. Let's go. Okay, this should be good. All right, so this is good enough. So there's 3 right there, and then we're gonna go all the way down. We're gonna go all the way down to -5. So let's say the point is all the way across here. We're gonna be drawing in 3D. This goes. It's gonna go behind it. So I'm gonna break that apart. And yeah, here. So this is gonna be -5 all the way down, and there's our point. -4. 3 and -5. And now let's draw this in 3D. Yeah, so to do that, let's draw our top part here and draw a parallel line like that. And this is going to go all the way down. And let's do this more down like that until this is parallel like that. And then we're going to have this line across here, parallel to that, a y-axis. And then behind it, we can have dashed lines, dash, 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 dash. And then this is going to be another dashed line like that. And then dashed line like that. All right, here. So I fixed that up and made it smaller just so we can fit this inside. It will fit the other one inside. So this one is going to be 3, -2, and -6. So it's also going to be below this, it's going to be below this floor. Because it's negative vertical, it's going to be, it's going to be -6 there. But now it's going to be in the front, and then we're going to go backwards there. So let's draw this out. So we're going to do, again, the z-axis. But it's going to be on the negative y. So we could have a short z, we could have a short y, like that. And then it's going to be on the positive x. So we can make this super long. There's the x, like that. But it's going to be on the negative y. So make it like that. So negative y. So we're going to go to 3 here. Let's say all the way to 3 here. And then we're going to go -2. We're going to go all the way across here, -2. And then we're going to go all the way back down, all the way until -6. So we're going to go all the way down. And we're going to go like this, -6. Like that. And then draw this in 3D. And well, this is the point right there, and this is going to be our 3, -2, -6, like that. And then we're going to draw this all in. Let's make this bigger. And now we're going to draw it in 3D, so it's going to go like that. So it's going to go all the way down until it's parallel. Well, this one here as well. Until it's parallel, so all the way down, like that. And yeah, this one across like that. So make this all the way down, like that. Yeah, so it looks something like that. Now we draw this in 3D behind it. So this is going to be all the way down, dot, 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 dot. It'll be all the way down like that somewhere. And this is going to be dot, 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 dot. And then dot, 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 dot. And yeah, here I just fixed it up, made it a bit smaller to match this. And yeah, so it looks like that in our rectangular box there. Well, anyways, let's continue further. So the following Cartesian product is the set of all ordered triples of real numbers and is denoted by this r to the power of 3, and this is the Latin capital R, usually written like that, which I sometimes just use r cubed there. And this Cartesian product, this is just written as r, let's write this in the Latin form, r x r times r, and this equals to the set, we'll write it like this, of all these points x, y, z, where x, y, and z are elements of real numbers. In other words, these are all just real numbers like that. So this is written like that. So this is the set where x, y, z, these are all just real numbers. Or it's a collection of all the points. And just for completeness, so this r times r times r, this is just indicating this is our r cubed equals all this. Alright, so now that we have this is just a set of all of these points, x, y, z, or of all these ordered triples, and we have given a 1-to-1 correspondence between points P in space and ordered triples A, B, C in R3, where these are just all real numbers inside here. So each point has a 1-to-1 correspondence with with these collection of triples right here, this x, y, z, and so on. For this A, B, C, and R cubed. So this is called a dimensional rectangular coordinate system. And notice that in terms of coordinates, the first octant can be described as the set of points whose coordinates are all positive. Remember, yeah, that's where all the positive axes are. In two-dimensional analytic geometry, the graph of an equation involving x and y is a curve in R squared. Yeah, curve, or just a line like that, it's just a curve. But in three-dimensional analytic geometry, an equation in x, y, and z represents a surface. So in 2D it looks like that. In 3D it's going to look like just an actual surface. So imagine this is in 3D. So a full surface like that. And we can illustrate this in example 1. So example 1, what surfaces in R3, or in this set of all real triples right here, are represented by the following equation: A, which is z equals to 3, and B, which is y equals to 5. Alright, so let's take a look at the solution to part A. This is z equals to 3. So the equation z equals to 3 represents the set, so all the points x, y, z, where z is equal to 3, and which is a set of all points in R3 whose z coordinate is 3. And this is just a horizontal plane that is parallel to the xy plane and 3 units above it, as in the figure below. So the equation z equals 3 in 3 dimensions, that's where all the coordinates have a z equals to 3 variable or value. So if we have this, let's just draw our our z-axis like that. And this is going to be our y-axis. I'll just make it a bit more 3D. So this is our y, and then this is going to be our our x, like that. And this is our origin at the 0 here. So this is our origin. And now we're going to go all the points that are z is 3. So in other words, we have to go all the way up to here, 3. So here's a 3 point. But it's a plane number, so it's going to go to infinity everywhere. So it's going to, let's just draw this in 3D. So it's going to look like this. And all the way across. Like that. And since this is in front of it, I'm just going to remove this. Remove this vertical. I'm going to put this like this. So this is above. And now it's going to go below, dot, 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 dot. Make the dot, dot better. So that's at the 3. And this is going to be dot, dot, dot. So that's, the axis is behind it. So we're drawing this in 3D. So it looks like that there. And we could write here, this is z equals to 3. And this is a plane in 3 dimensions, or R3, like that. So in R3. So yeah, typically when I'm writing this by pen, I'll write it like this in the Latin form. But when I type it out, I typically write it like this because it's easier, because there's no button on my keyboard for the Latin version. All right, so now let's take a look at the solution to B. So B was this equation: y equals to 5. So if z is equal to 3 is a horizontal plane, then y equals to 5 as well. It's going to be a vertical plane. So the equation y equals 5 represents the set of all points in R cubed whose y coordinate is 5. This is the vertical plane that is parallel to the XZ plane and 5 units to the right of it, as in the figure below. So if we draw our, this is our Z axis, and we're going to go across here. Let's say that's our Z. I'm going to put it something like this. There's our Y. All right, let's make it even further. This is our Y, and this is going to be our X, like that. And this is where Y equals to 5. So let's go all the way up to here, 5. And this is going to be a plane. So we're going to draw a line like this. Line all the way down. It's going to be behind it. Draw this in 3D just to make just a giant plane like this. Like that. And yeah, as before here, I just fixed it all up, made it like this. And as before, we got to draw the dashed lines for the ones behind it. So I'm going to erase this right here. Draw this across there. And then it's going to be dashed line. So this one's going to be straight across, and this is going to be dash, dash, dash. Like that. Yeah, so we have that line like there. And also we could shade this in. Like that, shade it in. So it's a plane. And shade this in. Like that. And yeah, so we have this equation as y equals to 5. And this is a plane in... So a plane in R3. Let's draw this better. Alright, so now that we have that, that's a vertical plane right there. But now let's take a look at just a quick note on context. Because this one here, we're asked to solve equation y equals 5 in R3. But if we're looking at 2 dimensions, so when an equation is given, we must understand from the context where it represents a curve in R2 or a surface in R3. So in example 1, y equals 5 represents a plane in R3, but of course y equals 5 also represents a line in R2 if we are dealing with 2-dimensional analytic geometry, as in the figure below. So if we have, yeah, this is just our xy axis. This is our x, this is our y. Then the line, if this is our origin 0, then the line is just like this. This is just y equals, this is the 5. In other words, this is y equals 5, and this is a line in R2. Alright, so now let's continue further. Now this section is added the title here. So equations of vertical or horizontal planes. So in general, if k is a constant, then x equals k represents a plane parallel to the yz plane. Yes, in other words, where x is fixed, so that's going to be a vertical. Yeah, this one's going to be a vertical plane. And then y equals k is a plane parallel to the xz plane. That's also vertical because it's a z. And then z equals to k is a plane parallel to the xy plane, and that's going to be horizontal, and so on. So in the earlier rectangular box figure above, actually before we get to that, I'm just going to write over here, represents a vertical plane, and this one's, whenever z is constant, horizontal plane, parallel to the xy. So in the earlier rectangular box figure, the faces of the rectangular box are formed by the 3 coordinate planes. X equals 0, this is the YZ plane. Y equals to 0, this is the XZ plane. And Z equals 0 is the XY plane. And also these right here, X equals A, Y equals B, and Z equals C. And we can see this if we just scroll up to that earlier rectangular box we had. So that's this part right here. And what I'm going to do is I'm going to add all the points here. So this is B. If we remove this A, it gets to this point. We'll just call this 0, B, 0. And then this point across here, this is our 0. I mean, no, that's going to be, yeah, actually, this is going to be, yeah, 0. So we're going to remove this B there. So it's going to be 0, 0, C. And I'll just put this as the origin. And then we have this part right here. Yeah, this part here is going to be this is when we take this A right here, but then we just remove the B as 0. So we're going to get over here, it's going to be A, 0, 0, like that. Alright, so here I just teleported back down here, and I just added here. So that same figure went over, copied below. So we copied here, made it a bit smaller, And now we could look at these 6 planes there. And this top part is where the z is constant. Actually, before we get to those, let's go this x equals 0, y equals 0, and z equals 0. These are the those are the 3 coordinate planes. Here, let's move it over here. So we have the 3 coordinate planes, and then we have also these extra planes. So if we look at the coordinate plane, I'm going to draw this in red, where we have x equals to 0. That's the yz plane, yz. That's in the background here. Let's make this not in front of it. So like this, like that. Yeah, and then etc. So that is this part right here. This is our x equals to 0, like that. And then the next one is, let's make it a different line here. So this is this where y equals 0. That's just going to be xz plane. This is y equals 0. Like that. So that's this, or y equals 0. Like that. And then this is a z equals 0 is at the bottom, where z is completely flat there at the bottom. Like that. And so on. That's our z equals 0. And then let's draw different colors. It's a bit hard to see, but just to illustrate. And now this is the x equals a, is when you have it all the way across this face. This is our x equals to a. And then y equals to b is all the way across this face here. And yeah, x equals to b, like that. Yeah, so it's a bit messy there. Then we have z equals to c. That's the top of this box. So again, z equals to c, like that. All right, yeah, so it's a bit messy there, but I think it's if you were watching the video, you could follow along. Yeah, just follow along how I did. But if you're just looking at the notes, it's gonna be a bit more complicated. But anyways, it just looks a bit messy, but I think it's good enough. All right, so now let's continue further. Now look at example 2, and this one has 2 parts, part A and B. And part A states which points x, y, and z satisfies the equations x squared plus y squared equals 1 and z equals to 3. And then part B says, what does the equation x squared plus y squared equal represent as a surface in R3? All right, so let's take a look at the solution to part A first. So because z equals to 3, the points lie in the horizontal plane z equals to 3 from example 1a. So if we recall example 1a, that this is our z equals to 3. So it's going to be somewhere along this there, but then we're also given an equation of a circle. This is just an equation of a circle. So because x squared plus y squared equals 1, the points lie in the circle with radius 1 and the center of and the center on the z-axis as shown in the figure below. So if we draw this out, we're going to have something that looks like this. This is our z, and there's our y-axis, our x-axis. There's the origin, and this is our point 3, and now we have it like that. I'll make it a bit shorter. So we have a point 3 here. And so that's a 3 on the z, but now we have x squared plus y squared. That's just a circle on this z equals 3 plane. So we can write it like this, draw it like this. So there's a circle. And that's just a circle there. And well, it's going to be behind this. So let's make this like this dashed. Let's try this one more time. All right, yeah, so just have it like that. So this is going to be our circle. Yeah, so it's going to be circle, and the equations are circle x squared plus y squared equals to 1, and z is equal to 3. All right, so now let's take a look at the solution to B. So B is here. So we're given, what does the equation x squared plus y squared equals 1 represent as a surface in R3, in other words, in 3 dimensions. And this is the same thing as this, but there's no z equals 3. So let's take a look at the solution to B. So given that x squared plus y squared equals 1 with no restrictions on z, we see that the point x, y, z could lie on a circle in any horizontal plane z equals to k. So the surface x squared plus y squared equals 1 in R3 consists of all possible horizontal circles, x squared plus y squared equals 1, and z equals to k. and is therefore the circular cylinder with radius 1, whose axis is the z-axis. So basically, we're not limited to the z equals 3. It could be on anywhere across. I'm just going to copy and paste that same graph here. Yeah, so I'm going to copy and paste that. And now we can remove this 3, so it does not have to be the 3. And it could be anywhere. And this is going to go all the way down. Yeah, we'll just go down here. It's down here. I'm just gonna make it on the positive axis, but it can go all the way down. And this is gonna be a cylinder like that. A bit better, like this. And then this is gonna be in 3D. So we're gonna erase this, put this down here, and then dot 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 all the way down. We'll actually keep going because it's a surface, not a 3D shape. So, I mean, not a solid, so it's not a solid, so then put all the line all the way down there, and we go dash, dash, dash. Same thing with this, dash, 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 extend it out, and just to make it in 3D, dash, 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 and then like that. And now I'm just gonna shade this in blue, just make it like this, or actually in red, shade it across, or it's a bit hard to shade, and then the inside shade it as well, like that. Yeah, just do that just to show it's a surface, and then basically we have surface, this is the cylinder, or this is a cylinder right here. Alright, so there's our cylinders, just typed it a bit better, so x squared plus y squared equals to 1. And yeah, so the radius here, yeah, so the radius across here is 1. Yeah, r equals 1 like that. Or instead of making it this way, just write r equals to 1 here. R equals 1, yeah, from there to here. So these are going to be 1, 1, etc. Alright, so now let's continue further, and now let's look at example 3. And this one states, describe and sketch the surface in R3 represented by the equation y equals x. So let's take a look at the solution. So the equation represents the set of all points in R3 whose x and y coordinates are equal. That is, if we write this set out, we'll write it like this. So this bracket x, and then x. Y is x, and then z like that. And again, this is because y is equal to x. So we'll just write them both as x. And this is where x and x and z. You could write it as x, z are all real numbers, or you could even write it as x is an element of all real numbers, like this, and z is an element of all real numbers, like that. This calculus book wrote it this method, or in this form, but you could write it as x and z as all real numbers, or x all real numbers and z all real numbers, like this, and then just close bracket like that. Now, this is just a vertical plane that intersects the xy plane in the line y equals x and z equals to 0. And the portion of this plane that lies in the first octant is sketched in the figure below. And because it's a diagonal line, I'm just going to draw this out like this. So the calculus book draws it. So it has the z-axis like this. Here's the z-axis. Yeah, so it's a z-axis there, and then it has the x-axis over at this side. Yeah, just fix it up. So x-axis over there, and then it has the y-axis over like this, y, and then I'll put the origin here, and that's just so that we could have this line better presented. So I'm going to cross this line here. So this is at the y equals x line, and at z equals 0. And then now we could draw a vertical line across. I'm just going to make it shorter, and then it's going to be like this. Bit shorter like that. It's going to look something like this. Make it vertical and parallel, and this is going to be like that. And again, because this is in 3D, let's just erase this, or we could just move it up like this. Actually, it's better just delete it and then start fresh. So it's going to be like this. This is going to go across like that. This is going to be dash, 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 dash like that. And then again, if we just shade this out in red like that. So that's the plane like that. And this is at the y equals x, in other words, at the perfect center there. So the same distance across. And we're going to write this as a plane, the plane y equals to x like that. Alright, so now let's continue further. Now let's look at distance formulas. Well, first I'm just going to look at the distance formula in 2D, and then we're going to extend it to 3D. So recall the 2D distance formula between 2 points, and basically what we have is like this. So let's say we have xy axis, just derive it here, and then we have a point here. This is point 1, P1, and this is our x1. Yeah, I'll call this P1, x1, and y1. And then let's say I have a point here, P2. This is our x2, y2, like that. So the distance between this and this, call this absolute value P1, P2, like that. So that's a distance. And then we could use Pythagoras, draw a right angle triangle, and then this distance here is going to be absolute value of y2 minus y1. This is absolute value of x2 minus x1, and then Pythagoras. Yeah, and here I just typed it out here, or just wrote it out. So then we just apply Pythagoras or Pythagorean theorem, and then square root. We're going to get P1, P2 is equal to the square root, and we'll only look at the positive square root, and it's going to be square root over this one here. Let's put it's for completeness. Well, yeah, if this is absolute value squared, it's the same thing as writing x squared minus x1 squared plus y squared minus y1 squared, like that. Whether it's absolute value or not, when you square it's going to be positive. It's going to always be positive. So let's just recall this formula right there. Alright, so now that we have this, and now the familiar formula for the distance between 2 points in a plane, this one above here, is easily extended to the following three-dimensional formula, and here is the distance formula in 3 dimensions. Yeah, so we have the distance P1, P2 between the points P1, X1, Y1, Z1, and P2, X2, Y2, Z2. This can be extended over, and it's going to be just P1. The absolute value P1, P2 is the distance. This equals to square root, and then this just extends it over x squared minus x1 squared plus plus y now. Y2 minus y1 squared plus z2 minus z1 squared. Alright, so now that we have this, and then we're going to go over a proof of it. So proof to see why this formula is true. So here we just extended it and added the z component here. To see why it's true, we construct a rectangular box as in the figure below, where P1 and P2 are opposite of vertices, and the faces of the box are parallel to the coordinate planes. So let's draw this all out. So if we have a z-axis like this, and there's a y-axis like that, and this is our z, like this, and then this is our x, like this, like that. And let's draw this just in the top here, just to get it high up so it doesn't interfere with the axes. So let's say this is our point. This is our point P2, and let's say we have a point across here. Well, so I'm just going to draw a box first. So let's say we have a box like this, and just move it even here. So we have a box like this, and then this goes down like this. This goes like that. So we have a box, and this is going to be parallel, parallel, until we have it at vertical, like this, and then we have this across like that. And then behind it, all the way at the bottom, this is going to be all the way behind it. Alright, so we have this, to make this a bit neater, or downwards more. Alright, and at this point here, we'll call this P1. This is going to be P1, P1, and this is going to be our x1. Well, actually, before we get to that, just move this over here so we have some more space. We're going to have P1. This is going to be our x1, y1, z1, like that. And now this point right here, we'll call this P2, like that. And erase this and draw it a bit bigger. Okay, so this is P2. P2 is our x2, y2, z2, like that. All right, so now we have this, and what I'm going to do is I'm going to consider this point here as B. This is our B point, and this is going to be as x squared, x2. So all we're going to do is drop this z all the way down until it matches the z1 there. y2 and then z1, like that. And this is, I'm going to draw a line across here, dash line across. And this is a perpendicular line, like that. I'll just fix that up. It's going to be like this, the perpendicular line. And now what we're going to need this point across here. From here to here, this is the point that we want. So this is, I'm going to write this as a distance. This is going to be P, I'm going to write this in red. So all the distances I'm going to write in red. P1, P2, absolute value. All right, so this point is B, and now this point here is our A. And I'm going to write this A as A is x2. So basically, it's going to be the same thing, this point here, but we're going to remove this, yeah, it's going to be the same as this one, but we're going to remove this x1 and replace it with x2. So it goes over to here. This is x2. This is going to be x2, and then everything else is the same. So it's going to be y1, z1, like that. All right, then now we have this a, b, like that. I'm going to write this as absolute value of a, b, like that. And again, this is, I'm going to write this here. This is another right angle. So we have two right angles across here and there. All right, so we have a, b there. Now we have this part here from the top to bottom. This is, we'll call this as P2B, like that. And the next one here is from here, this A to P1 at the bottom there. That is going to be our absolute value of P1 and then A. And these distances, this is just, well, this is a horizontal distance. Remember, it's parallel to this. And that just means, well, it's going to be x2 minus x1, the absolute value of it. So we could write this all down. So you could write absolute value of P1 A. So this distance is going to equal to absolute value of x2 minus x1. And then this one right here, AB, this is parallel to this y-axis. So this distance is just going to be the y's. So then we have a absolute value, or the distance AB, is equal to absolute value of y2 minus y1. And then the last one is this vertical component. It's just vertical is parallel with this. And so that's just going to be z2 minus z1, and that's our P2B. Like that. So we'll write this as P2B is equal to z squared, or z2 minus z1, absolute value. All right, so now that we have this set up, well, we notice what we have is, well, we have two right angle triangles. So we could basically find this distance, which is our P1B, and then we can solve this distance up top, which is P1, P2. So we have two triangles there, and I'll just change this back to red. So we have this distance right here, P1, and then B, like that. So P1B is down here. So that's the hypotenuse of this triangle, and then it will become the base of this other triangle, and that's the hypotenuse. So we can apply Pythagorean theorem twice. So because triangles P1, B, P2, so P1, B, P2, and P1, AB, so P1, AB right here are right angled. Two applications of the Pythagorean theorem give, and yeah, let's just write it out. So let's write our distance P1, B2. Oops, this erase this. So P1, B2 there. So we're going to have P, so absolute value P1, B2. I'm going to square it, just because Pythagorean theorem is a squared is equal to P1B plus P2B squared there. So this equals to P1B squared plus P, this is going to be P2B squared, like that. So that's this part right here, this, and this, as this over here. So that's what we have there. And then the second triangle is, this is the hypotenuse. And this hypotenuse squared is equal to this squared and this squared. So in other words, this part right here is going to be P1b squared is equal to P1a squared plus AB squared. And again, this is just this part. So in other words, we can throw this inside. So throw this inside here. So that's what we can put inside. And when we do that, we get here. So this becomes P1, P2 squared is equal to, and then we just replace this with this. P1a squared plus absolute value AB squared plus the distance P2, let's write this better, P2b squared. And we know what these all equal. Those are just these. A1 is x squared minus y minus x1. x2 minus x1, not x squared. And then AB is here, y2 minus y1, and then P2b is this one here, z2 minus z1, and that's all squared. So we could write this as equaling to absolute value x squared minus x1 squared plus y2 minus y1 absolute value plus z2 minus z1 squared. And since we're squaring, it's going to be positive, so we could put this all together. So thus, and also square root it just to get it all out of the way, and then look at only the positive of the square roots of P1, P2 is equal to square root, and write this as x, and then just write it in normal bracket, x2, x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And we could just box this all out like that. So there is our distance formula in 3D. Alright, so now let's just quickly double check, and if we scroll up here, yeah, so this is the one we were given. This is, yeah, the distance is just x squared minus x1 squared, and then plus the y's and z, and then all squared. So exactly the same thing as this right here. Now let's take a look at example 4. And this one doesn't really give a question, just because it's pretty straightforward. So the distance from the point P2, from the point P, which is 2, the coordinates are 2, -1, 7, to the point Q, which is 1, -3, and 5 is, so we can just apply this formula there. So PQ is equal to square root, and now the x2 minus x1, so that's going to be 2 minus 1. 2 minus 1 squared, then plus y, 2 minus y1, so we'll just have this -1 minus 3, or actually just for completeness, because this is x2 minus x1, just to make it the same form. It doesn't matter because you're squaring it, and it's always going to be the same. It's always going to be positive. So let's just go 1 minus 2. Just go from this as our x2, or second point, P2. So then this can be -3 minus 1. -3 minus 1, that's going to be, minus -1 is going to be plus 1. And then plus, the next one is 5 minus 7. 5 minus 7 squared. And now this equals 2, and well, it's square root. 1 minus 2 is -1, but you're squaring it, and it's always going to be positive. Just go 1 squared plus this one here, -3 plus 2, or I'll just for completeness, I'm just going to keep this in, -1 squared plus, and the -3 plus 1 is -2 squared, and then plus 5 minus 7, -2 squared. This equals 2 square root, and then this is going to be 1. -1 squared is just 1. -2 squared is plus 4, and then the next one, -2 squared is plus 4. Again, that's going to be 8 plus 1 is 9, equals to square root 9, equals to 3. Yeah, 3, or you could even have -3. So -3 times -3 is, also put that for completeness, plus minus. What is this going to be that? We just look at the plus side of it. Yeah, so just erase this. So just do completeness, because when you're just square rooting, it's you can have still -3 times -3, but you can't have a negative distance in this case because we're defining it as absolute value. All right, so now let's take a look at example 5, and this one states Find an equation of a sphere with radius r and center hk1. Actually, not 1, it's actually L. So Calculus book writes L lowercase, but it's just, for me, I like using capital case, just because it's easier. It doesn't look like a 1. This one here, I write 1 like that sometimes. So this is how it writes L lowercase, and I'll just write it as capital L. So find an equation of a sphere with radius r and center C, which is coordinates h, k, and L. So solution. By definition, a sphere is a set of all points P, x, y, z, whose distance from C is r. And you can see the figure below. So let's just draw this in 3D. So a sphere is, here's the z-axis like this, and there is the y-axis. This is our y, and there is our x, and this is our z, like that. And this is, we have the center here. The center inside is, let's say, C, and this is H, K, L. And then the distance across all the way to, because we're inside a sphere, to P of x, y, z, like that. Be like this, and then it's going to be always the same. This is going to be r, like that, and just draw this like that. And I'm just going to draw this, shade this in red. So it's a 3D sphere. Shade it in like that, something like that. So it's a sphere. All right, so we have this sphere like that, and the distance from C is going to be always, it's always going to be equals to r. And here I just move this over just to make the more in the center there, like that. All right, so that's actually in the center now of the sphere. So thus P is on the sphere if and only if the distance PC equals to r. And then if we square both sides, we're going to have PC squared equals to, well, r squared. And this equals 2. And remember, the distance formula is just we subtract the x's and the y's and the z's and so on and squared, and because we already we're squaring that, so we get rid of the square root. This becomes x minus, so this is the x, this is h, as k as the y, and so on, x minus h squared, and then plus y minus k squared plus z minus l squared. Yeah, so thus our equation of a sphere with radius r and center C, HKL is just this. So we can box this r squared over like that. So there's the equation of a sphere. All right, so now that we have this, and basically this result of example 5 is worth remembering. So we'll call this equation of a sphere. So an equation of a sphere with center C, HKL, and radius r is, and we'll write r squared on the other side. So we're just going to write this as x minus h, like this, squared plus y minus k squared plus, and then z minus l squared equals to r squared, like that. All right, so now in particular, if the center is the origin O, then an equation of the sphere is, so this is the C is all going to be 0, 0, 0. So that just means that the equation is just going to be x squared plus y squared plus z squared equals 2 r squared. Again, compare this with the equation of a circle, which is just x squared plus y squared equals to r squared. All right, so now this brings us to example 6, and this states, show that the following is the equation of a sphere and find its center and radius. So we have this equation, x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equals to 0. So solution, we could rewrite the given equation in the form of an equation of a sphere if we complete squares. First, recall completing squares. So if we recall right here, x plus a squared, this equals 2, because that's just a square. So this equals 2, well, x plus a times x plus a. So we're going to multiply x by x, and then x plus a, and then x by a, then a times x, then a times a. In other words, we have an a times x and an x times a. So this equals to an x squared plus 2a. And then the last one is a squared plus a squared. So x times x is x squared. Then x times a plus a times x is 2a. Yeah, 2ax. Like that. Let's erase this and move it. 2ax. And then the last one, a times a is a squared. Like that. Yeah, so the key thing is we have this 2a and then we have this a squared there. And that's what this x plus a squared is, becomes this. Yeah, so thus, we just need to write these x and these y's and the z's all in this form so we can complete the square. And what we'll do is now, so thus, so we have this, I'm just going to blank this out, thus, and let's just move over this x over here. Just for completeness, let's write it all out. This is x squared and then plus 4x. So we're going to write this as, let's write it here, x squared plus 4x, put a bracket just to separate it. And then the next one is this this y, and there's a negative 6y. So we have a plus y squared minus 6y. And then the next one is, this is going to be plus z squared, and then plus 2z. Like that, plus 2z. And then this 6, we're going to move it over to the other side. So it's going to be negative 6, like that. And now if we look at this, completing the square, so this part right here, there's a 2a there. So all of these have a 2ax, but we need to add a squared. So in this case here, we have 2a equals to 4. So that means a is equal to 2, and a squared is equal to 4. This means, yes, this means a squared is equal to 4. Oh, let's remove that arrow. So we have a squared is equal to 4. That's rated small. And now this case here we have, so this right here, this is, put an arrow here. All right, so go back to here. So this negative 6, that means we have our 2a is equal to negative 6. That means our a is equal to negative 3, and then our a squared is just going to be, well, positive 9, like that. And the next one is over here. Our 2a is equal to 2. This means our a is equal to 1, and a squared is also equal to 1, like that. Yeah, so what this means is, well, we need to add an a squared to each one, and then we'll also subtract one from each equation so that we don't change it. And then move that that additional a squared over to the other side. Just so, yeah, let's put it all over there. So what we'll get is, so we get x squared plus 4x minus, this is going to be plus a squared now. A squared is 4. So that's our a squared. 4, like that. Next one is, and then we're going to subtract by 4 squared as well. This next one's going to be y squared minus 6y, then plus a squared, which is 9. Plus 9, and we're going to have to subtract that as well. And then plus, the next one is z squared plus 2z. I'm just going to put this here, a squared, for completeness, plus 2z, and this is going to be plus a squared, is going to be 1, like that. And then at the right side is negative 6. So we want all these extra stuff that we added to cancel. So we just add these on this side as well. It's going to be plus 4. And then minus, this is going to be plus 4, plus 9, because they cancel. We make them the same sign, because it's on the other side. And they would cancel. So we're not changing anything. And then the next one is plus 1. Like that. And let's just add these up. So negative 6 plus 4 is negative 2. Like that, and then these two is 10. So then negative 2 plus 10, this is just 8. Like that. All right, so this becomes, and now this is completing the square, so x squared plus 4x plus 4, that just becomes x plus a squared, where a is 2. So this becomes x plus 2 squared, like that. Next one's going to be, this next one's going to be y, this one right here, a is negative 3. So we're going to have y, whoops, and go back here. So y minus 3 squared, and then plus the next one is, so we have this square completed, this a is just 1. So we get x plus 1, z plus 1, like that. z plus 1 squared, and this all equals to 8, like that. So this equals to 8, and remember this equals to r squared. And this whole thing is just an equation of a sphere. Equation of a sphere. Alright, so thus, and we're asked here, so we're asked to find its center and its radius. So this is r squared. So thus our center, I'll write thus, the center is equal to, and remember it's going to be the negative of these. So this is x plus 2. It's going to be the negative, because if we scroll back up to our equation here, negative h, the center is h. Negative k, center is k, and so on. So we do the negatives. So center is going to be negative 2 plus 3, so let's write a 3, and then negative 1, like that. And the radius is, I'll write radius. Radius, I'll make it capital actually. The center, and then radius. Radius is going to be r squared. I mean, r is just going to be, well, is equal to square root, square root 8. So here is square root 8, and this equals 2. Well, it's simplified. The calculus books usually does that. 4 times 2, so the 2 becomes, the 4 becomes 2. So 2 times square root 2, and we're looking only at the positive of the square root. So that is the radius, and we could just box out the center and the radius. Alright, so now let's take a look at the last part of this video, and that's example 7. And this one states, what region in R3 is represented by the following inequalities? And we have this. 1 is less than or equal to x squared. Yeah, x squared plus y squared plus z squared, and is less than 4. And we're also given that z is less than or equal to 0. So let's take a look at the solution. The inequalities can be written as, and basically we're going to take these two inequalities, these two, it's this is greater than 1 and less than 4, less than or equal to 4 and greater than or equal to 1, and write this, and then basically square root both sides. So what we'll do is 1 square root less than or equal to square root x squared plus y squared plus z squared, and this is less than or equal to 4. I'm square root 4, this equals to 2. So what we'll do is this basically equals to just 1 less than or equal to, less than or equal to square root x squared plus y squared plus z squared. In other words, that's a distance less than or equal to 2. And we'll only look at the positive because we're looking at distance right here. And these inequalities right here represent the points x, y, z whose distance from the origin is at least 1. So it's greater than 1, and it's going to be at most 2. But we are also given that z is less than or equal to 0. So the points lie on or below the xy plane. Thus, the given inequalities represent the solid region that lies beneath or on the xy plane and between or on the following spheres. Well, let's write the spheres, and we're going to write this as x squared plus y squared plus z squared equals to 1, and in between these two right here, and x squared plus y squared, and it's just equation of a sphere, plus z squared, and then the r squared. This is going to be r squared is just, well, 2 squared equals 4. And so now if we were to draw this out, this is going to be, let's draw it like this. Let's say this is our, that's it, I'll draw our z-axis like that. And then our y-axis, so that's a z, and we're going to draw our y-axis going across negative and positive. There's the y, like that, and now we're going to do the x-axis across here, and there's our x-axis. And now what we'll do is, well, it's going to be 2 spheres, distance 1, this is the origin, and we're just going to have a 1 here. I'm going to draw a sphere here with distance 1, or a circle, across this. Well, actually, because it's going to be behind that, so we're just going to write it like this. behind it, can be on these, can be like that. Alright, here I just fixed it up, made it like that, and the next one is going to be at distance 2, can be like this, and again it's behind that z-axis. Alright, here I just fixed that up, so it looks like that, and then it's a solid region, so let's write this, let's draw this out like that. It's going to be underneath this, and then it's going to be behind this, like that. And now let's shade it in. I'm going to shade it up top here. So make it look like it's 3D and shade it in, etc. Whoops. Or actually, I'll just shade it in like that. So it's shading it in. And now here, fix up the shading like that. So yeah, that's what it is. Just made it look like so it's an indented inside. And there is our, half of a sphere with a hole inside, but then it's cut off. So it's half of that. Yeah, essentially like a thick coconut here that's cut in half. Oh yeah, coconut with a thick skin there. And yeah, pretty interesting stuff. And that is all for today. And yeah, so hopefully you enjoyed. I'm just going to scroll back up. And yeah, I'll be continuing on this series in future videos on this vectors and geometry and 3D geometry and so on. Anyways, that is all for today. Thanks for watching. And stay tuned for another Math Easy solution.